So welcome everyone, and thank you for joining us today in our InfoSec seminar organized by the Information System Security and Assurance Management Department in Maharshan School of Management. We begin our February InfoSec seminar by acknowledging that although this seminar is being held virtually, Concordia University of Edmonton is located on Treaty 6 territory and a traditional meeting ground and home for many indigenous peoples, including Cree, Saulteaux, Blackfoot, Métis, and Nakota Sioux peoples. We respect and acknowledge this. We are pleased to welcome Dr. Alison Yakshan, our QS Dean of Management, Dr. Patrick Kamau, QS Dean of Graduate Studies, and Dr. Andreas Glizo, the Deputy Provost and Acting Register, who joined us today for this great InfoSec seminar. So, happy Valentine's Day. Today, we are pleased to introduce our guest speaker, Sebastian Fischmeister, to give us an interesting talk about on physics-based cybersecurity and lessons from commercialization. Sebastian is a professor at the University of Waterloo in NSERC Magna Industrial Research Chair in software for connected and automated vehicles, and leads the real-time embedded software group. Sebastian performs system research on joining safety and security for safety-critical systems. Key highlights of his research include a framework for real-time Ethernet dynamic binary instrumentation for time-aware systems, real-time runtime verification and attestation of hardware and software using side-channel analysis. He is now working on physics-based cybersecurity and zero-trust supply chain models. Sebastian is a licensed Canadian professional engineer and active in international standardization with SAE G19 and the global security guidelines with MITRE. Thanks, Dr. Sebastian, for being with us today and sharing your experience with us. Just two quick notes. During the presentation, microphones will be turned off to avoid interrupting the speaker. At the end, we will have 10 to 15 minutes for questions and the microphones will be turned back on. Please limit yourself to one question to give opportunity to other participants to ask. If we have enough time, please feel free to re-ask again. And please be sure to provide us with your name and email address in the linked form so we may send your attendance certificate of attendance. It's all yours, Dr. Sebastian, now.
All right. Thank you very much. Let me share the screen here and make sure that everything is working there. Can you confirm that you see everything and it's all good on your end?
Yes.
Excellent. Thank you very much for having me and for inviting me to give this lecture on basically a different approach to cybersecurity and alternative that can complement existing approaches. And I will talk about three particular aspects in this. One of them is to give a general overview of safety versus security, because there's often misconceptions about this, of how safety and security connect and interact. The second part will then be on how we use physics-based cybersecurity for intrusion detection, to give an idea of what is an interesting approach in this area. And the third part is then on physics-based cybersecurity for the supply chain. And overall, I hope that you take away from this lecture something on that there's a difference between safety and security, and both of them are important, and that there is an interesting new research topic out there that is evolving, which is physics-based cybersecurity, where there's a lot of opportunity to identify and understand and develop new techniques, methods, and tools. So let's first start with the context of this talk. The context is in the area of real-time embedded systems. And to understand what real-time embedded systems are, is you have to basically just understand your surrounding, and you have to understand that in a real-time embedded system, the correct value too late still causes errors. And that is simply the fact that because the universe does not wait for you no matter what you want to do. If you have an aircraft flying and you want to think that you need to recompute something, you need to restart the system, the universe doesn't care about it. The thing will just come falling down like a rock. And in this particular context, all of you actually know real-time embedded systems, because whenever you have written an exam, you know that even if you have the correct answer 10 minutes after the exam is over, it doesn't matter. You will not get any points for it. So let's jump in this context of these real-time embedded and safety critical systems into the first part on safety versus security. And this will be a short session on always, there's an observation that basically comes from working in that area, and then a couple of points explaining this. Number one, modern systems are beyond deep comprehension of the human mind. And to show you what I mean by this, let's look at a modern car. The cars that you drive to work and drive for pleasure are actually incredibly complicated. You will be surprised to learn that they have over 100 computers inside that individual car to make that work. And to show you more of the statistics, here, take a look at how code complexity, so basically software size, grew in safety critical systems over the decades. And when you look at this, we start with the Marina in the late 1960s, and life was great then, not only because the music was better, but also because the whole program for the Marina fit on a single page of paper. Just imagine going to work, printing out a single page of paper, reading it, and that's your whole program, and you can even understand everything. Any software developer nowadays will dream about this, because we have now millions and millions of lines of code. And you can see here the entry that the Ford 150 has 150 million lines of code. And you can see aircraft with millions of lines of code. And the growth in complexity is not stopping there. As we go to more and more, for example, AI and ADAS type systems, where you basically have computer-assisted functions, code complexity will rise. And my point is that we cannot really understand digital systems. And the reason is that the code complexity and the size are simply the challenge for us, that we did not grow up with it. Let me give you an analogy for this. If I ask you to build a bridge from Tokyo to Vancouver, I hope that none of you will bid on this contract. All of you will sit there and say that there's no way that we can build this. If I ask you the same thing in terms of complexity of code, you will have people line up outside of my door, banging on the door, shouting they will do it for half the price. And why is this so? The reason is that humans are very bad at intuitively judging logical complexity, as you see in software systems. And let me give you, because we have a mathematician or several in the lecture room as well. Let me give you this very nice example of a so-called busy beaver. The busy beaver is a theoretic problem where you basically build a Turing machine that has n states and m symbols. And the idea is to build a Turing machine that takes the most number of steps or writes the most number of ones. There's a number of different variations of this particular challenge. And I will use this as an example to hopefully demonstrate to you that judging complexity of something as simple as a machine that you will see is very hard. Let me give you here as a teaser the busy beaver with 2 states and 2 input symbols. How it really functions and what the notation means is not really that important. The point is that this particular system that you look at has 2 input symbols and can have 2 internal states. And now I have a tape where I can write numbers about the output of the alphabet, and can basically then try to build a system that runs as long as possible, as long as it halts in the end. Now, when you look at this busy beaver here, you can demonstrate that it takes 6 steps until it terminates. That's okay. 2 states, 2 symbols. Let me give you the example with now 5 states and 2 symbols. So I give you freedom to define freely 5 states that you can traverse around in, and I give you 2 symbols upon which you can react. And to make your life easier, I give you the busy beaver, which is here on the right side. And I can then let you now give you a couple of seconds to think about how many steps do you think does this busy beaver take until it halts? And I give you a hint. It's more than 6, obviously. It's more than 60. It's more than 600. It's more than 6,000, more than 60,000, more than 6 million. This busy beaver that you see here with just 5 states and 2 inputs takes 47 million steps before it halts. So in order to really have seen all the behavior, you might want to have to observe 47 million steps already in this busy beaver. And to make things interesting, let's switch it around. We look at a busy beaver with 2 symbols, 2 states and 5 symbols. And I can again let you guess, but you will not guess the number. It's more than 47 million. It's more than 47 trillion. You can even think of whatever number you think at, and will most likely be lower immediately. It is 10 to the 704. And that's only currently the best designed busy beaver for this particular challenge. And every thermometer that you program, every car that you program, obviously, every phone has way more states and way more inputs than this. And this is where my observation comes from, that when you have a system with hundreds of millions of lines of code, no human can fully comprehend what this system is doing. And the challenge is now, of course, that we start connecting these systems, and that causes the problem with cybersecurity because it makes attacks scalable. Whereas 40 years ago, if I wanted to attack a vehicle or any kind of critical infrastructure, I would have to walk up and manipulate it. Now I can sit 8,000 kilometers away from it, modify it, and then basically make it do my bidding, even if it ends up in a non-safe state. Another observation is that safety and security are 2 orthogonal concepts. I illustrate this by an example. Here you have a vehicle that is safe but not secure. It is safe because it has been developed up to the, at that time, established safety standards and safety procedures. So it was perfectly safe to operate, but it was not secure because a famous attack identified a vulnerability, how to take over portions of that vehicle, disable brakes, and so on. And millions of people were not driving this vehicle. It's perfectly safe, but just at that time, before the patch, not secure. Here you will see a vehicle that is secure but not safe. Nobody would drive this car except Colin Firth, who developed it. And why is it is safe? While it is secure, it's simply an old car that has no connectivity in there, so you can't really have a scalable attack. Why it is not safe is obvious. It's a bubble bath in there. As soon as you brake, take any kind of quick actions in that vehicle, you have all kinds of problems with this particular vehicle. So you can see that safety and security are 2 orthogonal concepts. Another observation, a difference between the 2, is that safety deals with the universe, security deals with people. What does this mean? Safety deals with the universe in terms of random faults that occur in your system. Because of that, we have a rich history of developing engineering methods and mathematical models to describe fault-tolerant behavior, to describe reliability and how likely it is for a system to fail. Because we can create models for random bit flips, and we can use them in our mathematical models to then calculate, for example, failure rates. Security, on the other hand, is people and attackers flipping bits on purpose. So any kind of assumption on, for example, the number of bits being flipped in a single component, and whether that, for example, can be covered by, for example, triple modular redundancy, is all of a sudden not valid anymore, because the security or the attacker can deliberately flip the number of bits required that makes any kind of assumption that you made in your model for reliability incorrect and obsolete. Another observation is that safety is static, security is dynamic. And I put there an asterisk on safety is static simply because there's a disclaimer on this particular statement. So safety is static because if you follow, for example, ISO 26262, which is a standard on how to develop safety critical vehicles or safety critical systems in vehicles, describes precisely the lifetime of developing a safe product. And you can follow this process and you can basically then end up with a safe product. And once the product is safe, it is always safe. Once you design it to be safe, it is always safe. Now I put an asterisk on there because the user always comes up with new ideas, whether that's like the Tightbot challenge or whether that is new, for example, insights on, for example, the use of asbestos. There might be always new insights that come up at some point that require an update. But fundamentally, it is relatively stable. And once a product is safe, it is quite safe for a long time. Security does not have this property at all. When you look at this graph here, you can see on the x-axis the years, on the y-axis you can see the number of vulnerabilities and exposures reported in the CVE database. And you can see that we have a huge upwards trend here. If you take the calculation, and this is only until 2019, and you can just extrapolate this, we get about 236 new vulnerabilities every week. Even just after this talk, you will already have 1.4 new vulnerabilities out in the field, and we will potentially that are potentially affecting your critical system, and you need to deal with this. Another observation is that the durability of systems that we have today, especially in the safety critical domain, and their connectiveness challenge assumptions that we have, assumptions that we have made and seen before. If you look at a mobile phone, companies consider this outdated within 3 years. I was shocked to actually see that one of the mobile phones that I have, after 3 years already, you don't get any security updates for it anymore. On the other hand, we are operating safety critical systems and real-time embedded systems for a very, very long time already. And this creates an interesting problem as we, for example, oh, and by the way, remember 236 new vulnerabilities discovered every week. So a lot of vulnerabilities as you operate systems for 20 plus years. And this creates an interesting problem of what I call the highly automated old timer that we will have in the near future, where people will be driving vehicles with autonomous functions or ADAS functions developed in the 2000s and then brought onto the market into the early 2010s. Who is providing updates for those? Who is making sure they still remain safe and secure? The companies that sell you the vehicle already made their money. There's little incentive for them to update these functions and maintain them. But something needs to be done, because if all of these vehicles suddenly become not secure anymore and can be exploited, then you have a big problem on the road. Another observation is that software is becoming the dominant problem for safety. We've established this by looking at the NHTSA recalls in the US. We also looked at the Transport Canada database and the RAPEX database in Europe. And basically throughout all the three databases, we have analyzed thousands of recall reasons. And you can see that the number of software-related recalls is drastically increasing. That's one of the reasons why the automotive industry is pushing so much for over-the-air updates, and other industries that deliver critical systems will follow as well. Another observation is, and the last one for this particular block, is that the attacker has an unfair advantage. Safety systems must always work. Attacks must only work once. What this means is the following. We've developed over the years in 2015 to 2018 the Renesas autonomy demonstrator, which was basically an autonomous vehicle developed by a number of colleagues here, where we had a large group where we developed an autonomously driving vehicle that was shown at CES. For this vehicle, Professor Janetsky and Professor Woslander developed like a complicated architecture that had to cover ego perception, environment perception, static and dynamic and static environment perception, mission execution, vehicle actuation, all of this to make sure that this vehicle works. Even when you develop all of this, you get so many corner cases that you have to handle. Here you see, for example, a corner case that is in the area of Kitchener-Waterloo near the hospital. And the question is, as you drive onto this road, are you allowed to turn left? No, not really. You're not allowed, seemingly don't be allowed to turn right. You're not allowed to drive straight ahead. So what the heck is going on here? But you somehow have to handle this because you can't have just your cars piling up there. You have cases like this. If your camera sees this, well, what is really happening here? Is there a truck driving into you in a couple of seconds? Or even these scenarios that happen in Canada, and somehow your vehicle has to handle this. However, an attack has to work only in one particular instance. Here you see an example of the famous sticker attack on stop signs, where basically, even if you have your autonomous driving vehicle, all you have to do from the attacker side is find a clever way how to place sticker on a stop sign to make that one stop sign be recognized as a, for example, speed limiter, and all your vehicles will just barrel through the intersection. And so this shows you, while on the safety side and the development of the system, you have to think and develop all of this because you want the system to constantly work. The attackers have just to find one corner case where they can try and beat your system and then exploit this. So as a conclusion on this part, safety and security are different properties. Safety and security interact. Modern systems must be safe and secure. Let's move on to the second part then. Basically, this work inspired us to develop physics-based cybersecurity. And in the first portion of it, I will talk about using it for runtime monitoring and intrusion detection. The problem actually started with me developing code for a modular robot at the University of Pennsylvania. So a colleague, Professor Mark Yim, they developed modular robots. It's a very nice little thing from my perspective. It's like a robot that can change its shape and basically adapt its shape based on the task that it needs to do. What I was looking at that time is, how do you develop an operating system that allows precise timing control so that the robot can perform actions that are coordinated even across all of these modules. And what I learned back then, and already and also prior to that already, is that debugging embedded systems is really difficult. If you have a defect somewhere in your code in one of these modules and this misbehaves, how do you figure out what's wrong? How do you understand why it's not working properly, and how do you debug this? You can't stop the system because suddenly your whole robot comes breaking down because you need the robot to be stable. And this led me to work on time-aware instrumentation and instrumentation of how do you debug system and extract information from systems without missing deadlines in real-time systems. And the idea fundamentally is for time-aware instrumentation is that as you have your program, you only instrument certain areas of the program so that you can extract as much information as possible without violating the deadline. And the nice thing about this work was that we were able to make a prediction as we started the work and say, if we succeed with this work, we would see a right shift in the worst case execution time profile, which you see on the right. Now, we worked through this. We developed the time-aware instrumentation on a number of occasions, and actually what was very satisfying from somebody who was used to developing system and already knowing exactly how the system is going to behave, to be able to make a prediction and then validate it with data from the field. So we instrumented different types of file systems for the embedded domain. We instrumented the one laptop per child system at that time. And we were able to confirm this particular redshift. But then luckily a colleague of mine was in the area of side channel analysis. And we came up with the idea and said, hey, can't we use physics parameters to understand what the system is doing? Can't we use indirect observations on whether the system is operating correctly and where the system is right now? And this led to the idea of using power consumption in computers to understand what the program is doing. And the problem was, can we use side channels as a novel data source? And originally we set out with debugging. And so the idea was to develop power tracing as a technology. So what we had is very simply our embedded system connect to a shunt resistor, fed that into a sound card, used the sound card as an ADC, and basically visualized the power draw of that particular target that we were assessing. And the question was, could we understand what the program was executing by looking at this? And I understand that there's a lot of work on side channel analysis for the purpose of attacking systems, extracting keys and so on. Here, the idea was really to develop something that the developer wants to use for debugging and tracing, and not as an offensive cybersecurity tool. So we were able to build just a very simple mechanism for this, and we were able to extract that information and tell you precisely where you are in your program by looking at the power traces. That led to much more work than afterwards. And so this work was in 2013. That led to more work than afterwards, where we said, oh, cybersecurity would be an interesting aspect of this. Can we use side channels not to attack systems, but to protect systems? And so what we looked at is, can we use the power consumption to identify safety and security violations in a system? And let me give you an example here. Here you see, for example, the power consumption of a microcontroller that is controlling a door lock. And it is receiving first an instruction from the key. It is then decrypting the key portion to understand whether it's a key that is authorized to open the door, and then it's executing the door unlock procedure. And these many wiggles that you see here, this is essentially the authentication portion to check whether this is really an authenticated user that is then, through an authorization check, allowed to perform that action. Now, if you are an attacker and you clone a key and you have a vulnerability in the system, you would go in and just try and bypass this particular function. But the interesting thing is, if you bypass this function, it would show up in the power draw. So what we developed is a method of observing the power consumption of your door lock. And here you can see that in the one case, the authentication is present. And here, when you perform ARC injection on the system, the authentication is missing. And that means you could take arbitrary systems and start observing the power draw and learn something about the cybersecurity state of this particular system. Is it currently functioning normal? Is there a defect that is well explored in the area of machine condition monitoring? Or is there a cybersecurity incident currently with this system? We started to develop this more and more over the years to look into power trace assisted attestation to basically build a verifier that sends either out an alarm if something goes wrong, or if sends out an okay signal that everything looks good. Then we started looking into, well, that's an interesting idea. can we see whether we can turn this into some more practical applications and scale this up in potentially a product? Well, we first started off, a colleague, a student of mine started a company for drones and then later on for cameras. And we basically used the platform that he has in his company to start instrumenting. And we also looked at this, and it was a lot of fun because when we developed this initially in-house here, the very first mission was to drop a beacon on an iceberg, and a student had a lot of fun going out on a fishing boat and basically dropping a beacon on an iceberg there. We then also used it to instrument and understand and trace systems in the autonomous vehicle that we developed in the CES and then the year after as well. And then for a driving platform that we developed in the lab, which is great because it has no safe state. So we could have different types of cyber attacks on it. And the vehicles couldn't just simply stop and think what to do next. And so this was then shown with Denso at CES as well. And through this, we then got to the state that we say, oh, let's make this more and more real and build this into larger and larger platforms. And we actually built it into a defense platform as well in Canada. And there is one lesson that I could take away from this is if you develop physics-based cybersecurity, you really need to understand the input space for your system, because we got a case where basically the industry partner called us and said, hey, your system started smoking because we simply underestimated the current draw of the system in one particular usage scenario. But overall, it was great, and it led us more and more into productization to really develop these boxes that you can see here now that we deployed with municipalities in Canada in order to assess the integrity of computing systems, of wastewater treatment systems, and other types of basically any type of computer or OT system that you can connect to it. And how easy this is, I want to show you in this particular brief video here, where you see here a wireless access point, and what you do is you basically just place this box in between and you route the power draw through this box. This is one of the larger, the previous generations of this, and basically now you have fully installed it. Over a couple of reboots, it learns the model. Now you can see an attack on the system, and this basically modifies the firmware. The next time the firmware gets booted up, it will recognize that the boot process is different, the power draw is different, and it will send a notification alarm to a security operations center where you can triage this. Here you can see StackStorm that then can lead to a concrete action for example, the security personnel in that particular center. And here you can see really how we got from something that was originally, oh, can we monitor a door lock, to over many years something that, hey, you can plug this into any computer and now we can start monitoring the system. So the takeaway for physics-based cybersecurity for runtime monitoring is that side channel information provides a very interesting channel for defense. There are many more side channels that are available. We looked at power draw. There might be ultrasound. There might be temperature. There are many more that have not been really fully explored yet. But it's interesting because it's tamper resistant and an independent signal to any other host-based or network-based intrusion detection system you have. It can complement those. And the problem, of course, is on the other side is the data capture is much more complex than a pure software-based approach. So developing the technology requires more resources than a pure software-based approach. However, because we have a number of graduate students and researchers also here, there's a lot of interesting new avenues that you can take this, new types of information channels, new algorithms, new types of integration between a physics-based signal and a standard-based cybersecurity signal. Disaggregation of physics-based data that you can capture from these systems. A lot of opportunity, a lot of interesting projects. And with that, I will go to part number 3, one area that is also very active right now in my group. And that is supply chain cybersecurity. We have a fundamental problem in supply chain where you have a very long and very deep supply chain and a lot of opportunity for attackers to modify this. Because an attacker might sit in any of the many parties along the supply chain to introduce and stage a vulnerability that they can later exploit for an attack. And the intent might be just simply financial motivation to replace a functioning chip with a cheaper chip to make some money. But it might also be that somebody might stage a vulnerability in, for example, Canada's power grid, and then thereby have the ability to afterwards ask for ransom or have the ability to strategically turn off portions or attack it in a particular way whenever they please. And it's actually not difficult to do this. I mean, every undergraduate from the University of Waterloo who has like an ECE degree can do these things, because all you have to do is sit in there somewhere in the supply chain and perform modifications. And it can be as simple as overproducing without proper quality controls, or it can be something as fancy as reflashing firmware and having a backdoor in that firmware. The reason why we have this as a problem is because industry mostly uses a trust-based supply chain approach. What does this mean? Step one is when you want to buy something from a supplier is you send them a questionnaire and let them fill out a questionnaire. And basically you ask them, are you cyber secure? And the problem with that is you basically just ask them, oh, do you wear the right t-shirt to work? And after you filled out the questionnaire, some companies already stop there and just accept everything that they receive from that particular supplier. Some companies go even a step further, that they test a couple of samples that the supplier gives them and sees, are they actually good? And after this, everything is fine, right? Everything is good until it is not. Because it just needs one particular actor in a chain of potentially 30 companies before the product lands in your critical system, in the energy grid, or in your car, or in your aircraft, in order to make a modification that will then later on have an exploitable vulnerability. And how easy this is shown with a couple of examples here. Monte Elkins showed that all it takes is a $2 microcontroller that you solder onto a Cisco switch in order to have backdoor access to these systems. And if I wouldn't circle the red area on the motherboard, you wouldn't even know which chip to look at. How often do you open the Cisco switches that you order for your company or for your critical infrastructure and open them up and see whether they have integrity? 2015, Harry Krantz got convicted because what he did is he marked up chips. He basically sold a lower grade chip as a higher grade chip by modifying the marking on them. These chips ended up in helicopters. Helicopters crashed. They were investigated, and they found that he actually sold them marked up chips. A very interesting comment is from the law case is that the company, meaning Harry Krantz's company, sent the chips for an outside laboratory that basically said it passed all military testing. Just June last year, a person pled guilty in the US to have sold $1 billion of fake Cisco gear to the US government and military. To me, this is honestly a mind-boggling number. $1 billion of gear. That individual made over $100 million in profit, had I think 20 storefronts, different fake companies in order to sell this gear. Finding all of this gear now, tracking it down and replacing it costs many times more this. If you currently buy a Samsung 980 Pro SSD, you actually have a chance of getting a counterfeit and potentially a modified one. So this tells you that even the very high-end electronics like SSDs can have counterfeit and modifications. And then we enter the realm of concrete attacks, like talk-to attacks, where you can buy Cisco mod chips, where they have shown that they can load arbitrary firmware onto a Cisco device. And not only Cisco devices, they can also bypass Intel boot guard with this. And again, the question is, how often do you investigate the systems that you buy once you have approved your vendor or your supplier? Some people are just there for upgrading and swapping components. And then there's the infamous super micro attack. And I'm not here to argue whether it happened or it didn't happen. The much more important point is that Trammell Hudson showed that this attack is technically possible. And that alone is already reason to investigate supply chain cybersecurity and take that topic seriously. On the other hand, it is amazing that the company Supermicro lost 43% of value on the day that the first piece from Bloomberg was published. And finally, to show you another concrete example there is, which is just again mind-boggling to give you an insight into how these tactics work. L3 Communications Display Systems had a problem where they had sold 400 display systems to the C-130s and C-24 military aircraft, and they experienced a lot of failures in the field, even including one incident in operation. What they found out is that the supplier that they had gave them chips for the assessment, but these assessment chips were hand-picked genuine chips. So when they performed the questionnaire and then the initial assessment, all of these parts were hand-picked and genuine originals. The remaining 6,000 that they then ordered were all fakes. And of course, that shows again the problem of a trust-based approach where you initially vet the supplier and then afterwards you trust them on an ongoing basis. And how big is this problem? Well, ERAI shows that we have 14 new counterfeits reports published every week. So let's look for a defense model that is more sophisticated, that does not allow this kind of trust-based approach to immediately subvert your products. So we have this long chain, and as I mentioned, the attacker has a lot of opportunity. The idea is to develop mechanisms like we have in networks, but for products and electronic parts. Basically, a physical bogus part firewall at your intake on the procurement side to assess electronics and ensure that your corporation is free of tampered, modified, and changed electronics. You also want transport security and spot checks on there. And the main challenge is, of course, when you perform these checks, they should be non-destructive, black box, and vendor agnostic, because you don't want to have everybody change the system just to make it possible to check it with your firewall. So the fundamental question is, how do you then pick between these two systems? One of them is a real and one is a counterfeit. And what we developed is a physics-based approach where we use echo reflectometry to assess the internals of electronics and tell you whether they are authentic or not. Here's an example. Imagine you stand in front of a cave and you shout into the cave, back comes an echo. If you shout into the cave and the cave has been modified maliciously or by defect, the echo that comes back is different. We use this principle to develop and send a low power, high frequency electromagnetic pulse into the electronics and listen to the reflection to assess authenticity. Here you can see the productization of this technology with the company Paletronica, which is a spin-off from the University of Waterloo. So initially you see that we assess that Z80 chip, which is a common chip used in safety critical systems in Canada. And basically all you have to do is place the chip on this particular tester, you push a button, and 41 seconds later, you get the result. Now, there might be other approaches to do this. What is truly unique is that you can use this technique also for assemblies and basically put a whole network assembly, for example, on this here. You can see a full network card being placed on there, and it follows exactly the same approach. You push a button, you say what type of device it is, it assesses it and compares it to a profile and tells you whether this is an approved one or not. Let me give you some use cases that are publishable. We assessed FTDI microcontrollers on the open market, bought 220 chips from 7 different vendors. From these, 120 chips, 54% were counterfeit. We identified them with 100% accuracy on there. What we basically allow you to do with this type of technology is to not only verify trust, but verify your supplier, but also verify your supplier's supplier. And how good it is not only can we identify counterfeit, we also can detect defective and non-functional chips. We also use this for the problem of diminishing manufacturing sources and material shortages used in safety critical systems that have a long operating time, like for example the fighter jets and other type of infrastructure. And we used in this to, for example, distinguish between Z80 chips that were from an approved vendor and unapproved vendors, and we were able to identify a clear separation between those. And we were able to, for example, again, see here how clear the results are with these 2 point clouds that are counterfeit and tampered chips, and we have authentic ones. And a very interesting one is that one of the sellers sent us actually one authentic one in the hope that maybe we would test this one and then accept all the other ones, but basically the other ones are counterfeit. So we were able to identify multiple bad actors in the supply chain as part of the project. Another case is now in the energy sector, where we look at systems that are used, for example, in nuclear power stations and other types of systems for control. We were able to assess the system and identify, for example, an implant, which you see this little spider that is soldered onto the back there of this system to identify tampering in this particular use case. To sum this up, supply chain cybersecurity is a blind spot that we clearly have at the moment because everybody's using a trust-based approach, but trust-based approaches were the best thing that we could do. Now we can do better. And what you can see that we develop, and like this whole idea of using physics as part of supply chain verification, is going towards a zero trust supply chain. And that is the new standard. And again, there's a lot of opportunity for new development and new technology and a lot of research. I want to close with 2 lessons that I learned from this. And one of them is over the 25 years by now of research in the area of systems and applied research. And this is more to people who are currently starting out their research to give them an idea what gives them interesting and challenging problems. Often when you build systems and you perform research, you're somewhere in the valley, especially when you do applied research, you're somewhere in the valley where you have an idea, but it's somewhere not really there with the application, but it's also not really there with the pure theory side. And you can then choose, if you want to challenge yourself, what you want to do with this. You can get up on the more theoretic side, you add much more rigor, but you should be able to derive general, deep, long-lasting insights from that technology that you develop. And things like, for example, time-aware instrumentation, how programs change as you extract information from them. In my work went into this direction, and it was very interesting and satisfying. However, if you're interested more on the application side, then the main point is relax assumptions wherever you can. Originally, when we developed this, we were looking at microcontrollers. We were looking at very structured programs. Then we relaxed the assumptions to look at general computers and HVAC systems and so on. The results that we got were no longer as nice as the pure results that we started out in a much more rigid system, but the application was much larger of this. And so when you are in systems research and you're somewhere there in the middle of neither here nor there, think about to challenge yourself and climb up one of the hills on either side. And one other part is for all of you who think about somebody takes your paper and new technology and immediately copies you and rips you off. My experience is it's a very long path from a new technology to a product. At least it's very, for the technologies that we developed, but it's also very rewarding to get from an idea that you have in a paper that wins awards to something that you can put on a desk and test and see in reality tested on a number of systems. And with that, I thank everyone and want to give a couple of minutes of time for questions and answers. Thank you very much.
Thank you so much, Dr. Sebastian, for this great presentation. So please, if you have any questions, please go ahead. Yes, Michael, please go ahead.
Yeah, actually, not really a question, just a comment. This was really cool. Thanks, Sebastian. I lead the information security team at the University of Alberta, so I joined this because I have no idea what physics-based cybersecurity means, and you did a great job explaining it. And I was telling my team, like, you guys drop what you're doing and get on this call.
Thank you very much.
There's some really cool stuff that you're doing. So thank you.
Thank you.
Thanks, Michael. Any questions?
With the one where you had the overloading because of power draw, did you just solve it by limiting the power, or did you have to put better capacitors?
So basically, my training is basically computer science in background, and I've worked with a colleague and one of my research associates and also co-founder in Palitronica. He's the electronics guy, and so he can tell you everything, how he had to adapt the shunt resistor and basically modify it now that he can accept larger demands of the target that we were measuring. It is interesting. I can tell you what is really cool about this physics-based part is that you can, like, we have a new project starting where we bring in people from mechanical engineering who never thought about cybersecurity, and all of a sudden you tell them, hey, look, what can we use? How can we use this or that in order to get an indirect measurement of a system? And you can involve colleagues that you would have never thought of collaborating with before. And so for your particular question there is, I know that Carlos made an adjustment on this. We had to make a new shunt resistor board and in order to extract the information without getting it to burn up.
Thank you. Angie, please go ahead.
Hi, Sebastian. Thank you so much for really, really cool presentation. I think this is one of the most interesting conversation I've heard about physics-based cybersecurity. The question I have for you is, where can we get a little bit more information about physics-based cybersecurity? Because I haven't heard about that concept until now, and It sounds very fascinating.
Yes. So I didn't put a lot of citations and papers into the talk to keep it basically at a particular level. Fundamentally, you can look at all the work that is used on side channel attacks and immediately just twist your thinking and think about how can you use it not for attack purposes but for defense purposes. Yeah. And the typical approaches are immediately to think about, oh, how can you use some physical aspect for runtime monitoring, or for example for intrusion detection, or for example as we do on the supply chain for identifying counterfeit implants modifications on these systems. How can you use it for example, we have a paper now out there, how we can use power side channel to identify backdoors and undocumented commands in systems as well, in order to find things like, for example, if you understand port knocking attacks, or basically the port knocking defense, in order to hide some functionality in the system, you can use the power draw of a system to see whether the system reacts to something. It's basically, there's a literature out there in the area of side channel analysis. There's literature out there. I'm happy to send you an email with papers, and then basically you can dig on there. But the fundamental part is to switch in your mind the idea of saying, oh, I use power readings to extract a secret key, to oh, I use power readings to defend the system, to identify if somebody attacks it. And again, this is only for power readings. You can do this for a number of other channels as well.
Great. Any more questions? Any more questions? Yes, Robin?
Did you have fun doing this?
Oh, well, absolutely, yes. And after, I mean, I'm doing research since 1999, since my master's. what is one of the most rewarding things is to then take an idea where you write papers and really try and push them into an application and into the field, because you will learn so many limitations of this that you don't know when you write the paper. I mean, from things like, reconfiguration, reflashing, how does that affect the system? But also to cool new things that you can try out because you simply then have the real platform and you can try and attack the platform. And it's just, I enjoy it a lot. It's a lot of fun.
Always makes the job better.
Yes. Yeah. No, I mean, it's fun. Yeah.
Great. Any more questions? Okay, so thank you again so much, Dr. Sebastian, for this great presentation. And thank you all for attending the InfoSec seminar. Again, please be sure to provide us with your name and the email address in the linked form. I reshare it again, so we may send you a certificate of attendance. We hope to see you all in our next InfoSec seminar on March 13, 2024 at 12.
Thank you very much for having me.
Thank you.
Thank you.